Okay, hello everybody, global economics, and yeah, we are through with all the stuff I in general want from you within your term paper, and now we switch a little bit more to a theoretical part, and yeah, so also setting on the models we already know. Remember here, actually also talking about the Phillips curve at, oops, where we are here. We, for example, used the AS curve within the AS-AD model. And what I now want to do with you is that we shortly recapitulate the ISLM model. This is, yeah, also still one of the working horses in general, talking about the effect of economic policy, of the impact on an economy. So you have seen, or almost everybody of you have already seen this in the macro course. I will now go through this model in a more general way. We had until now discussed this more graphically and then with some easy linear functions. But of course, this model can also be used in the nonlinear case, and also doing such a general analysis using only the assumption that, for example, consumption is increasing if income is increasing, or that investment is qualitatively decreasing if interest rates are increasing. Now we are using, so to speak, only the direction of the effects and do not use directly the linear model. But on the other hand, I think I also that we are really then on the good prepared for the next argumentation within the model. I will go through quite roughly through some examples, but then we want to talk especially in more detail in this model about monetary policy. Okay, so again, what was the ISLM model about? In general, we looked at two markets within this model: the commodity market, so to speak, the real world, and then the money market, because money is the central good in the economy for exchange. So almost everything what we are exchanging, there is in between an exchange of money. And looking at these two markets, yeah, we then make an assumption about the equilibrium. And this is also the reason why we call it ISLM model, because at the commodity market, there, when you remember the concept of the circular flow and the sector of the financial institutions, there we said in general, we have an inflow into the financial institutions of all savings, and then all these savings are somehow repacked, and out of this financial institution sector, then we can provide all the credits for the investment in an economy. And then in equilibrium, these two volumes of investment and savings are met. And therefore, investment equals savings. Therefore, we call this then the IS. And out of this, we will derive in a minute the so-called IS curve, where we obtain then a dependence between output and interest rates. And at the money market, on the other side, well, there in general, we look at supply and demand. We assume a money demand function, especially the Keynesian money demand function, depending on income and interest rate, and the money supply, which we quite easily model because we just say the money is provided by the central bank with a certain level. Okay, then let's go to the commodity market. Well, in general, we look within this model at the overall economy from a demand side approach. And this then means, okay, let's take then also the demand approach, the expenditure approach for summing up the overall economic performance within a country, and this is GDP. What is GDP? What are we collect in GDP looking from the demand side? And this was consumption plus investment plus government expenditure, where we said that consumption in general is positively dependent on income. This is the argumentation via normal goods. You know, also in the microeconomic case, normal good is defined that demand increases if income is increasing. And that we have a negative dependence of investment on interest rates. And here also I used the Fisher equation that within these investments we also see the sum approximately of expected inflation plus real interest rates. So here I have it, real interest rates. And as a third variable, we have as an external number which is somehow set by the government. This is always then in democracies discussed every year within the parliament. How much do we want to spend in the next year? And in order to be a little bit simpler, we do not care about the last part, which we had the trade balance exports minus imports. This we skip at this point to have the model a little bit easier. Maybe in the end we have time that we also can add this. In the micro introductory course, we have used this also only as a fixed number, that we have some trade balance, but of course this part will depend on, for example, exchange rates. And so one can introduce a new variable, adding these trade balance and then depending on a new um, variable. But at this, we will not look at this part. Well, and then this means within this equation here, we just have an external variable, which is a given number, government expenditure, and we have some functional dependence between investment and interest rates and consumption and income. And this equates from the demand side approach overall income. So this functional form gives us a general dependence between income y and interest rates. Well, and now we do not want to use specific formulas for these dependencies here, but only the general assumption that we have a positive dependence, and also we know that the marginal consumption rate is between 0 and 1, and this means every additional euro we have, that we do not spend 100% of every additional euro, but less, some between 50, 60, 70, 80, 90%. As I said to you, in Germany, the savings rate is 10%. So then this number would be around 0.9. And positively, and that we have in general a negative dependence on investment. Well, then we can use the concept of the total differential. What was again the total differential? The total differential in the introductory course of macroeconomics we had when we were talking about the quantitative theory of money. This is something like a general derivative of some functional form. And I don't know, have you also used the total differential in your introductory course of mathematics? So where you have some function, now depending on more variables, not only on x, but let's say on x and y. Because then what is the overall change of our function if all variables are changing simultaneously? This is the question, and this is the general question. We do not want always only make partial analysis, that we fix everything only and assume only that one variable is changing. Overall in the economy, we know that in reality all variables are changing simultaneously. And therefore this is somehow one of the main mathematical tools which we use when we want to analyze in general a model. So the total differential defined is something like a general derivative. And then, of course, not surprisingly, we find within the total differential all single derivatives. So small d means a delta, means df of x and y, means the total change of the function. That this is quite easy. Well, you know, if you have the one-dimensional case and a function f of x which looks like this, what is then the derivative? The derivative is just the slope of the tangent of the function in such point. So this is f prime of x0. So if we have now a multidimensional or a two-dimensional function, what does this mean? Then we have, so to speak, two tangents. We go in two directions simultaneously. So this is then the derivative with respect to the first. This is, so to speak, the direction. Where is overall f moving if only x is changing? This is the direction. And then we multiply this direction with some small number, because we want to know how far are we moving? So, and this small number in mathematics is just a differential move. So this here we call it dx. So this is a very slight, a very small step of x in the direction of the derivative with respect to x. Well, but if simultaneously also y is changing, then this means we have to add also the change in the direction of y. This is geometrically just adding two vectors. So then it is df dy times dy or del. Here you have to be a little bit careful. The sign for a partial derivative, this is a stylized d, which is called del. So hopefully I could have explained that it is not really something complicated, but what you can really think of what it is. Or maybe hopefully I can somehow draw this. So in this direction we have f of x and y, and this would be x and this would be y. And then this two-dimensional function, I think something of like this you have maybe seen in school, is looking like some mountains. And then this would mean, okay, in some point, oops, x0, y0, this is then the functional number. This is the value of the function at this point. And then due to, if I am at the peak of a mountain or somewhere else within the surface, then I go from here in the x direction and in the y direction. And the overall movement would be then just adding up these two vectors. And these are very small vectors. And this is then written down just within these total differential. So again, it is something like an overall, a general derivative. Well, and we know that given this functional form, only y and I are my variables. Everything else is set, especially g is a fixed number. And this means taking the total derivative of this functional form or the total differential would then mean this is, the left side is quite easy. There I have only the y. So this is dy equals, here I have some functional dependence. So derivative with respect to y of c times, again, how far do I step in the y direction? Plus, here I have the dependence on the other variable. So di with respect to interest rates times the interest rate. Well, and the change or the derivative of a fixed number is 0. That you have also learned. If f of x is 3, then f prime of x is 0. So let me write it down. dg but this is 0 since it is a fixed number, since G is a fixed number. So then I have this here. Well, I know that the derivative of consumption with respect to income is positive and within 0 and 1. Or it is within 0 and 1, then it is, of course, directly positive. And here I know this number is negative. Then I can solve, oh, this shouldn't be an R, this should be an I. Oops. Then I can solve this equation, subtracting this part and dividing, or the other way around, and dividing by dy, that I then obtain the derivative of interest rates with respect to income equals 1 minus marginal consumption, the derivative of consumption with respect to y, divided by the dependence between investment and interest rates. But here, I know this is a number within, between 0 and 1. 1 minus any number between 0 and 1 is again a number between 0 and 1. So in general, it is positive. This number I know is negative, and then I have a positive number divided by a negative number. Then overall, I know this is a negative number, and thus I know that from the commodity market equilibrium, I know that in general, I obtain a falling curve representing the dependence of interest rates and income. Because any function which has a negative derivative is a monotonically decreasing function. And so in macro, we have derived this graphically. We can assume that in general, these IS function representing the commodity market equilibrium is just a falling function. And if we want to model this linearly, then we could use such a model, a linear function. But this would be then again a special function. Okay? Hopefully you remembered a little bit. Now we did it from a theoretical basis in the mathematical way to derive it. Okay, then let's go to the money market. Here we will do it in the same way. Oh, on the next slide I did the graphical, but let's do it in the same way that we also use the mathematical approach. So in general, again, we have our money demand function. Positive dependence in general, no, not between 0 and 1, only just positive, and dependence on income, and negative dependence on interest rate. Money supply, especially real money supply, because in this part of our theory, we are in the Keynesian view, and there we say we have sticky prices, no price adjustment. So prices are fixed. and then real money supply is then by assumption given that we say, okay, the central bank can set nominal money. This is printing money, or also via the money multiplier, that we can say we can set the level of provided money within our economy. Nominal money given by the central bank. And then the equilibrium condition is just small m, real money, equals money demand. And here I had the graphical derivation, but I will also provide the analytical in a minute. How did we derive the dependence between y? Remember, m over p equals L depending on y and I. This is the equilibrium condition. That given some income level y0, this is our starting point. Then we are going just to the money market, and within the interest rate money amount diagram, we know here is a negative dependence. This we set to a fixed number, any income, let's say an income of 4 billion euros, GDP of Germany roughly, trillion, sorry, we are in the English course. So a fixed number, this dependence is negative. This means the derivative of money demand with respect to interest rates is negative, so it has to be a monotonically decreasing function. This is the blue line here. Money supply is a fixed number. Since we have on the horizontal axis money supply, this is some fixed level capital M over P. And the cut of both, this is supply, this is demand. The cut of the two is the money market equilibrium. So what does this money market equilibrium now implies? It says, well, this is an equilibrium given y0, given some specific income. Let's assume this income is within the interest rate income diagram, some fixed number which we can find here. Then this equilibrium point fixes us an interest rate level which corresponds to this income level. So this means I0 is corresponding to Y0 is just one possible money market equilibrium. And now we ask for all possible money market equilibria. And therefore now we change this income level Y0 to Y1, where we assume y1 is larger than y0. What does this mean then for our demand curve? Well, we know that the dependence on income is positive. Well, on the axis, we don't have a y. So the y is fixing where do we find our curve. If we now do not look at any point at our demand curve, then this means, since we have here a positive dependence, that for all point on our starting demand curve, if we increase now income due to the positive dependence, it has to be higher than before, and therefore it is shifting upward. So a demand curve, depending on a higher income than the starting one, has to lie above the first one. Then, of course, our money market equilibrium is changing. This means we have to use a higher income since y1 is larger than y0. And from equilibrium, we also see that the interest rate is increasing. So to y1 corresponds now a higher interest rate. So this would be another possible money market equilibrium. Well, and then we might make the thought experiment that we say, well, let's do this calculation now for all possible incomes. For another y2 larger than y1, y3, and so on. And we can even decrease the income with respect to y0. Overall, we obtain then an increasing dependence from the money market between interest rates and income. Let's do it analytically. There we have M over P is LD depending on Y and I. Again, the total differential would mean we have to calculate the change of real money. But again, real money is set by the central bank since prices are fixed. This is a fixed number. The derivative of a fixed number is again 0. Fixed number given by the central bank, also fixed prices. So the change would be 0, or let's write it down in this way, dm over p. This is 0 equals, now again we have a function depending on two variables. Partial derivative with respect to income times a slight change direction in income plus partial derivative again with respect to interest rates times a little change in interest rate. Well, this we again solve for the dependence, the change of interest rates with respect to income. So this means we subtract this on both sides. Here we have the 0. So we obtain minus del L del Y times dy. So we obtain a minus sign. This is still on the right side. And then we are dividing through the change of income. So we obtain then, hopefully I do it right, di is then dl, del L, del Y divided, is it the right direction? Let me do it a little bit slower. Otherwise, I always do it wrong. So then we obtain del L del I di equals minus del L del Y dy, and now dividing by dy and dividing by del L del I. Now it's okay. So we obtain di over dy equals minus del L del Y over del L del I. So, and now again, we use these two dependencies. This is positive, positive dependence on income. This is negative, negative dependence. Positive number over negative number is negative, but we have a minus sign here. Minus times minus is positive. So we obtain the positive dependence, and this is an increasing dependence between interest rates and income. So again, the analytical part. Okay, then having these general dependencies from the money market and the commodity market, we put this together and come to the overall equilibrium of our economy, the cut of the LM curve and the IS curve, simultaneous equilibrium of the economy, where we then have our equilibrium income and our equilibrium interest rate. Let's now think of how should I do this now. This I have already done at the other two slides. Okay, then let's look at the general solution of this model. What would happen if we are doing monetary policy? Since I have already done the calculation, general solution with monetary policy. Monetary policy means that we are now externally changing the money supply. So the central bank decides to increase money. This we have massively done in the after the financial crisis. Then the especially European Central Bank and Fed really started to buy with central bank money, government bonds at the capital market. Yep. In the end, it means printing money. So this is just creating money because the ECB is buying or has bought the government bonds with its own money. This was a huge money creation process. This means just starting to print money, so to speak. So with monetary policy, so an increase of money. smaller. And for this, yeah, I have enough time. We will do a little bit algebra. So remember, small m was m over p. Oops, this should be still a small letter. So let's do this again, what we have already done. Let's take now the differential, total differential of both equations, but now also, especially this one is changing. So also since P is fixed, real money supply is changing. Now dm is larger than 0. Remember when we have derived just the dependence between interest rates and income at the money market, we said, well, this is a fixed number and therefore it is 0. Now we say this is externally changed, so we have a change there. So then again, we obtain dy equals dc dy dy plus di di. This should be fixed, so no change. And here we have now dm equals dl dy dy plus dl di di. Oops, here is some variable missing. Well, what we now have is a linear system of two variables and two equations. Our variables are the change in income and in interest rate, and the commodity market equation and the money market equation are our two equations. The change of money, this is monetary policy, this is now a given number. And well, what we want to know within our model is if we increase the money supply, what kind of impact does this have on the overall economy? So what is the impact on the economy, especially on income? So what is the effect on GDP? This is what we want to answer now analytically. So let's now rearrange these two equations a little bit. So two equations. Oops. Two variables, di, dy. Then we obtain 1 minus marginal consumption times dy. This we have put there, minus di di equals 0. Okay, so we have subtracted this, took out dy, and oops, we also subtracted this. Here we just leave it, but we put it the other way around. So then we have dl dy dy plus dl di di equals the external change of the monetary base. So, and hopefully you remember something like this: 3x plus 4y is 20 and 5x minus 6y is 13. What you have to do if you want to solve for x and y. So we want to have here the impact of the change of money on the of the total income. So within our linear system here of two equations in two variables, we want to get rid of the variable di. In this case here, what do we have to do if we want to get rid of the y? I think something like this you have done in school and in your introductory course, or solve this for x and y. So what we have to do here? We want to get rid of the y. Yep. Yep. To subtract 1y, 4y, but then we have the y just on the other side. It hasn't then vanished. Okay, maybe it's too far away, but if we multiply on this side, or you have the idea? Yeah. So if we multiply this with 6 and this one with 4, then we obtain 18x plus 24y is 120 and 20x minus 24y is 62. Hopefully I'm right. And now what can we do? Yes, we just add these two equations and then we obtain, and generally you rewrite the first one. 18x plus 24y is 120, and the next one is then 18 plus 20 is 38x plus minus. This is what we have done. This was the reason why we have multiplied with the coefficients in front of. So plus 0 equals 182. And then we obtain x star 100 or 91 over 19. So the same we are doing here. We want to get rid of this. Then we have to multiply the first one with the coefficient of the second one. So times del L del I, and this one the other way around, times del I over del I. Okay? So then we obtain 1 minus dc dy times this one, del L del I dy minus di di del I del L del I di equals 0 times some number is still 0. And the second one, del L del Y times di over del I times dy minus, now the other way around, but it is of course the same number, plus I times I, and now This is not 0, so di del I times dm. Then again, we have here a minus, so we can add up these two, and we obtain, now it will be a larger one, 1 minus dc times del L del I plus, so plus this coefficient, and then large brackets, times dy equals this plus this vanish. This is what we wanted to have, and 0 plus this is still this. So di del I dm. So what we want to have is what is the impact of a change of dm on income. So we are dividing by this, and we are dividing by this. Then we obtain dm dy dm equals di over I over, and since I can copy this. The processor is coming at its end. Maybe it would have been faster when I have written it. I think the hardware is about 8 years old or something like this. Oh, I can't do this. Oh, maybe. Let's do it. I'm almost done. Digitalization is not always faster. Okay, so and now you ask, maybe you have some question marks. Well, what is it all about? Why has he done this? Well, we know very much about the signs of the derivatives here again. And let's go through all this. So, first one, positive or negative? Is? Yeah, positive or negative? It is negative. It is, yeah? It is. We know that this is a negative number. So, this one, money demand on income, positive or negative? Positive. Again, this we already have, negative. Money demand on interest rates, negative. Consumption on income, positive, and some additional one, consumption on income, positive, and between 0 and 1. So overall, 1 minus a positive number between 0 and 1 is it is a positive number. So a positive times a negative number is negative. A positive times a negative number is negative. The sum of two negative numbers is the sum of two negative numbers. is still negative. The division of a negative number and a negative number is positive. Minus divided by minus is plus. Yeah. So overall, we have that this is positive. And so then we have analytically shown that this, what it is intended by the central bank. Well, we are providing more money, and of course, we can qualitatively argue. Well, if everybody of us has 100 euros more, then we start to spend, and at first, the prices are not adjusting. So, if we start to demand more, then production will increase. So, this then here we have found within our analytical model. Well, now I can use this. Later on, I will mainly talk about monetary policy, but since I have this already, let's now use this in order to do fiscal policy. This means an increase of government expenditure. So, and now I take my rubber. This means now we have a positive G. And now we just change this everywhere. It is not that much. This is now a 0. And here we now say this is when we take the change. It is not 0. We say, well, the government in Germany just has decided to increase government expenditure by 500 billion. I'm always mixed up. 500 billion euros. So we have here DG. Still, we want to get rid of these numbers here. Then we obtain here a 0. And this is now changed. We have multiplied now with the dependence of money demand on interest rates. DG. This feeds through. So then this is gone and I need, oops, this one. Hopefully this is now a little bit faster. Not really. Or can I do it like this? This is better. Again, we are doing everything, our calculations are the same, only that now, oops, we have in the upper part the dependence on money demand on interest rates. So only this I is changing. But everything else stays the same. And also the dependence of money demand on interest rates is also negative. So also for fiscal policy, we obtain also a positive dependence. Sorry, this has to be changed. That now we are doing fiscal policy. And now we have also analytically shown this positive impact of fiscal policy on overall income. Yeah, and maybe you can imagine that this kind of concept you can also use if you have not only two variables, but three, four, and so on. And overall, in the end, these are then general equilibrium models. And of course, this is what a good model is then about. If you not always have to use specific functions, because a dependence on the demand or the supply side of a specific function means, of course, always very strong assumptions made on reality. Of course, we have some general functions. I think from microeconomics, you know, something like Cobb-Douglas production functions or something like this. Or maybe I've shown you for the guys who have done trade, assess function, I don't know. Um, there are some general functions which are used in general to do then econometric analysis. But at the first step, from a theoretical side, we really want to argue only about the dependencies and then hopefully to get reasonable answers doing all this analytic stuff. And I think you are now at your fourth, fifth semester or something like this in your further studies that you at least once have seen such analytical tools. Because somebody of you wants to go further within a master program, maybe also in a quantitative master program, and then I think it is a good thing that you have seen this. Well, you need not to do it in your term paper. Okay, I think through this we can go a little bit faster because all the guys who have already participated um, uh, in macroeconomics have seen this. This is then the general graphical derivation. What happens if the central bank increases money supply? Money supply is again a parameter of the LM curve. Where do I find it? Oh, I can maybe quite fast show it. This would then mean in the argumentation, let's take this in purple, this would just mean this shifts to the right, a larger money supply. So if here M prime over P and M prime is larger than M. This means just this vertical line shifts to the right, and this would mean that all these equilibrium points, since we haven't changed money demand, this would mean that all these equilibrium points shift downward the money demand curve. And this means this would be I0 prime to our starting income. Y0 corresponds now a lower interest rate. So this one here, but this has to be done for every income again. So also this shifts down and this shifts down. And in the end, we know that the LM curve is overall shifting downward. And using this graphically, this downward shift means that we end up within an overall equilibrium where we have an increase. Remember, this effect is our positive dy over dm is larger than 0, which we have shown analytically 5 minutes ago. But we also know here from a graphical point of view, this you can then also do because your linear system, you can of course also solve for I. If you do not want to get rid of the interest rate, you can just multiply the first part with the right coefficients, and then you get rid of income. And this means that we have a decrease in interest rate. And here downward, then again, I gave you the general qualitative argumentation. What happens within our economy? Well, if M increases, I get the right shift of LM. This means that a given income now corresponds to a lower interest rate. So I obtain a lowering of interest rates in my overall economy from the money market side. But then I step to the commodity market. What means a lower interest rate in the commodity market? This means that investment is going up. But a higher investment, since investment is one component of total income of GDP, means that a higher investment pushes overall income. And though also from a qualitative argumentation, of course, I also get these positive dependence. Okay, and then, yeah, we have another 50 minutes. Maybe we can then just calculate these two little examples. This was an increase of money supply. This is the same or only one? Oh, sorry. Oops. So let's skip this one. And here we have this, and that I have enough space to do the calculation. 12. Oops. Well, and actually, well, actually we have done already everything because we have solved our model already. That we can use in general this formula, or let's, no, this was fiscal policy, and we need this one here. This is our money multiplier, and well, we should determine the simultaneous equilibrium. Let's at first skip this and do it in a minute if we have enough time afterwards. But let's use this formula here, because we just want to have the impact of a 5% increase of money supply. We have, for simplicity, just a price level of 1. So M over P is just M. And the price, and 5% times 200 is just a change of M of 10. So, what is the derivative of investment with respect to I? This is our investment function. F of x equals 100 minus 200x. What is f prime? Mhm. So, and in the end, it is then, no, not minus 1, but here, minus 200, of course. What else do we need? dc del y. And we are here. 0.7. What else? Del L, del I. So what happens if we take the partial derivative with this part? This is maybe the difficult one. This is? Pardon? No. We are taking the derivative with respect to the interest rate. So then, since we are calculating here a partial derivative, then this is, in this case for us, just a number. Any fixed income. And the derivative, again, of a fixed number, 0. And then what is the partial derivative? Not 0, but we have here a dependence on interest rates. Minus 1000, okay. And what else? Del L del Y we need. There also we have to look at this function. 2. So now we have everything together and obtain dy dm is minus 200 divided by 1 minus 0.7 times del L del I minus 1000. Oops. Plus del L del Y was 2. Del I was times minus 200. So overall we obtain minus 200 divided by minus 0.3 times 1000 is minus 300 plus minus 400 and this ends up then minus 200 over minus 700. Why is this very low? I've done this the first time. This would be then only, oh, this is okay. 2 over 7. And then we have dy equals 2 over 7 times dm, and dm was 10. So 2 over 7 times 10 is 20, 20 over 7 is roughly 3. But we have to admit, we have to be careful. This functions only since we have here only linear functions. Otherwise, this provides only the direction. If you then, because of course a function is then moving maybe in a curve upward. But this calculation is only possible since we have linear given functions. Okay, we have 8 minutes left. Then let's maybe also calculate this. Well, now I make some. I think you have done this. Let's try it. Then I'm interested in. Let's do a real-time experiment. So solve. And what do we have? Y equals, oops, here we are. Anyway, this doesn't function. So C plus E plus G, I plus G, 300 plus 0.7 times Y. Y, 300 plus 0.7 times Y plus, what do we have? 100 minus 200i plus 50 was it? Government expenditure, okay? And we have 200 equals 2 times y minus 1000 times I. Solve this system of two linear equations for the variables I and y. This looks quite good. So now you are done. So I do this in this course. This was just an idea because, well, why should I do all this calculation? Well, but what is now really, really important using this, first of all, you have to make a reasonable prompt. You have to really formulate your problem exactly, because still AI is a stochastic approach. And also, unfortunately, sometimes it is miscalculating some things. It is not a mathematical program. But if you have quite simple mathematics, then I started to use it some month ago, because they implemented now mathematical programs within ChatGPT, within Grok, and so on. So you can, quite rely that you will obtain the right answer. But what you still have to know is, when you see in the end this result here, that you can make a look at it and say, well, okay, it is reasonable what I get here. The numbers what I get here are reasonable. So you still have to know what you are doing. But in the end, I think it was right what we have here. Then let's copy the output of ChatGPT in our slide. Oops. How was it? I think somehow this. No. How did I get in the new version the snipping tool? Again, I have to look it up. Windows Umschalt S. Windows Umschalt S. There it is. Zack. And here. Then let's copy this again. What I'm doing here. And I only want this, nothing else. And then this one, and here we have it. And oh, here we are already. So Windows Umschalt S and the solution. 1 minute. Let's just go through the calculation which ChatGPT has provided. Okay. Simplify this. Combine everything, adding up. 100 plus 300 plus 50 is 450. And then he has solved for y. This is another method to solve a linear system. that you solve at first for one variable and then feeding in this variable in the other equation. With this equation here, we substitute this in the other equation, which was just given by 200 equals money demand, feeding in this recalculation. Oops. We obtain the dependence on I. This I have missed here, so a little bit longer. Windows Steuerung S. So let's do it from here. Oops. Then we end up, this seems also right, here solving for I and then going back, feeding in I in our other equation, and we end up at y equals 700. So that it was, and you